Hi everyone, we're in Unit 4, which is Applications of Derivatives, and here is our first lesson where we will actually see some applications of derivatives. It's called Modeling and Optimization, or Extreme Value Problems. In sections 4.1 to 4.3, we learned about extreme values, we learned about intervals of increase and decrease, concave up, concave down, all of that kind of stuff. We're now finally going to get a sense of what that means and what that gives you. Okay, and so as mentioned, this is 4.4, Modeling and Optimization, or they're also called extreme value problems. And here is the general method for solving extreme value problems. This is kind of like your recipe. Step 1, draw an appropriate figure and label the quantities relevant to the problem. Step 2, find a formula for the quantity to be maximized or minimized. This is called developing a mathematical model for the problem. Step 3, using the conditions stated in the problem to eliminate variables, express the quantity to be maximized or minimized as a function of one variable. Step 4, find the interval of possible values for this variable from the physical restrictions in the problem. This can be done using the graph of the function or the equation. Step 5, use techniques to obtain the maximum or minimum. Use calculus to identify the critical points and endpoints, and you can always use the graph to verify. So what does this look like? Let's start with example 1. So it says find two numbers whose sum is 20 and whose product is as large as possible. Okay, so we want to maximize the product of these two numbers. So we'll start off with a let statement, and we will say let the two numbers be x and y. Step 2 in the recipe says find a formula for the quantity to be maximized or minimized. This is called developing a mathematical model for the problem. Now notice it says whose product is as large as possible. So the formula for product of these two numbers will be product P equals x times y. Okay, and we want to maximize the product. Okay. Step 3 says using the conditions stated in the problem to eliminate variables, express the quantity to be maximized or minimized as a function of one variable. So this product function, guys, see how it has two variables, x and y? We want to have it just in terms of one variable, oftentimes just x. We'd like to get it, excuse me, just in terms of x. So we have to come up with another equation involving x and y, and that's where find two numbers whose sum is 20 comes into play. We know that the two numbers have to have a sum of 20, so they have to add to 20, like that. Okay, and then if we get y by itself, you will get that positive y is equal to negative x plus 20, and I'm going to take that formula for y, and I'm going to plug it right in here for y. So our product function becomes x times negative x plus 20 and so the product function, if we multiply this out, is going to be negative x squared plus 20x. That's a negative quadratic. Okay, step 3 says using the conditions stated in the problem. Nope, we already did that one actually, sorry. Step 4, find the interval of possible values for this variable from the physical restrictions in the problem. Okay, so we need to find an interval for the x values, basically. Okay, and so x and y are any two numbers whose sum is 20 and whose product is as large as possible. There's no real restrictions on x here. Okay, so x can be between infinity and negative infinity. Okay, and those are kind of like the endpoints of the function. Okay, and the reason why I'm saying that is because hopefully you'll recall from before that extreme values either occur at the endpoints of a function or at the critical points. Okay, and the critical points are where the derivative equals 0 or does not exist. So we have to find the derivative of this product function, which is negative 2x plus 20. And notice that that exists everywhere. There's no problem points for x. But it equals 0 when you set this equal to 0 and solve. Negative 2x equals negative 20. X equals 10. There's our critical point. Okay, and so to determine the extreme values, we need to test the critical points and endpoints in the original function in this case it's the function p, to determine the extreme values Okay, and so we've got endpoints of negative infinity and infinity, so we want to determine what's the product of the two numbers as x approaches negative infinity. I mean, technically, we would be doing the limit of the product function as x approaches negative infinity, but I do sort of shorthand notation like this, and I sort of write it as, okay, what's going to happen to the product as x approaches negative infinity, like that. And similarly, what's going to happen to the product as x approaches positive infinity? And then what is the product at the critical point, x equals 10? Okay, and so we're plugging those values into this original product function. So imagine putting negative infinity in there. We'd have negative infinity squared, which is positive infinity, but then the extra negative out front. It would be negative infinity plus 20 times negative infinity. So that's going to go to negative infinity. If I put positive infinity in there, I'm going to get this. Infinity squared with a negative out front plus 20 times infinity. Okay, so the infinity squared with a negative out front is actually going to dominate the linear term, so this is going to go to negative infinity as well, even though 20 times infinity is pretty big. The squared dominates that linear term. And finally, what's the product at the critical point when x equals 10? We would have to go negative 10 squared plus 20 times 10. Got to get the 20 in there. That's going to be negative 100 plus 200. The answer is 100. Okay, and find the two numbers whose sum is 20 and whose product is as large as possible. This is our largest product. The endpoints go to a product of negative infinity, which is small in value. Okay, so we can say the maximum product, or the max P, is 100 when x is equal to 10. And therefore, y is equal to get y, you take your x equals 10 and you go and plug it back in here. Y is equal to negative x plus 20, so it would be negative 10 plus 20, which is equal to 10 as well. Okay, so the two numbers are 10 and 10. They have a sum of 20, and they give us the largest product. possible. Okay. And the last thing we can do with this question is look at the graph of p. So if we plot p versus x, it's a negative x squared. When x is 10, the product is 100. When x is 0, if x was 0, it doesn't matter what y is. 0 times whatever will give a product of 0. And if x is 20, I'm looking at this factored form over here now. If I put 20 in for x, I would get negative 20 plus 20 is 0. So x equals 20 would also give a product of 0, and the graph is a negative x squared, so it's a parabola like this. Okay, and you can see that we get our maximum product up here at the critical point where the derivative is equal to 0. And at the endpoints, the product goes to negative infinity, just as we got here and here. All right, so there's example 1. Let's try example 2. It says find the dimensions of a rectangle with perimeter 100 meters, whose area is as large as possible. Okay, so we have a rectangle. And we could say the length is x and the width is y. Like so. And we want to maximize the area of this. Okay, so the area of a rectangle is length times width. We could have used L and W here. I just used x and y, so it's going to be x times y. And we want that just in terms of x, so we have to come up with another equation involving x and y. And it says find the dimensions of a rectangle with perimeter 100 meters. Perimeter is the distance around the outside of the rectangle, and so that would be 2 x's added together and 2 y's. That equals 100 meters. Which, if you divide both sides by 2, we could write it as x plus y equals 50. And so y is equal to negative x plus 50, and we are going to go and plug that in there for our area function. So the area of the rectangle is now x times negative x plus 50, which can be written as negative x squared plus 50x. And we need to come up with an interval for this. Okay, and so x, because it's the length of a side, has to be greater than or equal to 0. Can't be negative. I suppose it could be 0, but then we wouldn't really make a rectangle, but it's not mathematically wrong to have x equal 0. Okay, and notice, guys, that y has to be greater than or equal to 0 as well, which means negative x plus 50 has to be greater than or equal to 0. Which, if you add x to the other side, means that 50 is greater than or equal to x. So x has to be less than or equal to 50. We get that from this equation here. You have to look at your x value and see what it does to your y. So if you put something in for x that's going to start to make y negative, y is a side length as well. That doesn't make sense. Okay, so that's how we can get the interval of x values. In step 4, they say find the interval of possible values for this variable from the physical restrictions in the problem. Okay, so we're finding the interval of possible values of x. So it's got to be greater than or equal to 0 because it's the length of a side, and it has to be less than or equal to 50, otherwise it will start making the y length negative. Alright, so there's the interval. These are our endpoints, which we need to check later, and extreme values occur either at the endpoints or critical points. So let's get the critical points. You find the derivative of the area function, which is negative 2x plus 50. Find where that equals 0 or does not exist. Negative 2x plus 50 exists everywhere. There are no problem points for x. And it's equal to 0 at x equals 25. So there's the critical point. And over here we are going to test the endpoints and critical points. Okay, in the area function, so we're interested in what's happening to the area as x approaches 0 or equals 0. What happens to the area when x hits 50, and what happens to the area at the critical point, x equals 25. Okay. We're trying to find the dimensions of a rectangle with this perimeter whose area is as large as possible. So we're looking for the max area. Okay, so if I put 0 in to the area function, sometimes it's easier to use the factored form here, guys. So imagine putting 0 in for x. Okay, you'd get 0 plus 50 is 50, but then you'd have 0 on the other one. So it's 0 times 50, the area is 0. If I were to put 50 in there, you would get 50 times negative 50 plus 50, which is 0. You'd get 50 times 0, which is 0. Okay, that's not maximizing the area. So it looks like our max area is going to come from the 25. And I'm going to put 25 in for x, and then it's negative x plus 50. So negative 25 plus 50. So it's 25 times 25, which is 625 meters squared. So we can say, therefore, the max area is 625 meters squared when x equals 25 meters, and therefore y, which is equal to negative x plus 50, negative 25 plus 50, y is also 25 meters. Okay, and so it's trying to point out to you that a rectangle, when you maximize its area, it actually ends up being a square. A special kind of rectangle, it's the square that maximizes the area. See how it's 25 by 25. So that's kind of cool. All right, let's try example 3. What is the smallest perimeter possible for a rectangle whose area is 64 centimeters squared? So we have a rectangle again. Let's call this length, width, length, width. What is the smallest perimeter? So we want to minimize perimeter, and the perimeter of a rectangle is 2L plus 2W. Okay, so we want to minimize the perimeter of this rectangle, and we know that the area of this rectangle is 64 centimeters squared, and the area of a rectangle is length times width. Okay, and so this is how we can get another formula involving L and W. So we could solve for L or we could solve for W. I solved for W. W is 64 over L. And we are going to take that expression and plug it right here. So our perimeter function becomes 2L plus 2 times W, which is 64 over L. And so our perimeter function is 2L plus 128 over L. And we need to come up with an interval for this. So L has to be greater than 0 because it's the length of a side, and it can't equal 0, otherwise you'd be dividing by 0 right here. So L has to be greater than 0, and then we look in this equation here and say, are there any L values that don't make sense? Are they going to start making the W values negative or something like that? And really there's no problem like that, right? Because W is just 64 divided by L. So really L can go off to infinity. Mathematically, that's consistent. You're not going to make W negative. Okay, so even if L is really, really big, that would just mean that W is really, really small. And so you could think of like a ridiculous rectangle where L is like this and W is just a little guy. And, okay, so you could have a rectangle like that, right? Okay, so there's the interval. Those are the endpoints. We also have to find the critical points. Okay, so that means we have to find the derivative of the perimeter function and find where it equals 0 or does not exist. So I'm just going to write 128 over L as 128 times L to the negative 1. And now we will do P prime. The derivative of 2L is 2. And the derivative of this is negative 1 times 128, which is negative 128, L to the negative 2. Which is 2 minus 128 over L squared. Okay, and we want to set that equal to 0. And solve that for L. Okay, so if we add the 128 over L squared to the other side, you would get 2 is equal to 128 over L squared. And then cross multiply and get 2L squared equals 128. Which means that L squared is equal to 64, which means that L is equal to plus or minus 8. Okay, but L has to be greater than 0, so we would reject the negative and just say L equals 8. That is a critical point. But then we do also have to keep in mind that we have to find where the derivative does not exist. Here's the derivative. L equals 0 is a critical point as well because the derivative does not exist at L equals 0. Okay, but that's actually not in the domain either. We're going to deal with that by exploring the endpoint of 0. So we can actually even reject this one. Reject. Not in domain. And similarly here, reject -8 because it's not in the domain. So now, over here, let's test our endpoints and critical points. Okay, so we can't actually equal 0 because then you'd be going 64 over 0, but we could sort of get a sense of, it's kind of like you're doing the limit, like what's happening to the perimeter function as L approaches 0. So what's happening to the perimeter function as L approaches 0? What happens to the perimeter function as L approaches infinity? And what's going on with the perimeter at the critical point 8? So if I imagine putting 0 into my perimeter function, here's my perimeter function. 2 times 0 is just 0, but we end up getting, so you end up getting like 2 times 0 plus 128 divided by something close to 0. That's going to be 0, but 128 divided by something really close to 0 is going to go to infinity. That means the perimeter is going to be really large, and we want the smallest perimeter possible. Okay, so imagine putting now infinity into our perimeter function. It would be 2 times infinity plus 128 over infinity. 128 over infinity is 0, but 2 times infinity is infinity, so that's not minimizing the perimeter. So it looks like it'll be at the critical point here again. Perimeter for L equals 8 is 2 times 8 plus 128 over 8. 128 over 8 is what? 16 plus another 16, so that looks to me like that's going to be 32 centimeters. So we can say, therefore, the minimum perimeter is 32 centimeters when L is equal to 8 centimeters, and therefore W is equal to 64 over L. So 64 over 8. W is also 8 centimeters. Wow, so this rectangle turns out to be a square again. So the square minimizes perimeter, maximizes area. Okay, and if you want to get an idea of the graph of this perimeter function, we have to use y. So our perimeter equals 2L, 2x plus 128 over x. Graph looks like this. Let's do window. X goes from 0 to stay at 20. And our minimum perimeter is 32, so why don't we go to a y max of 100 and see how the graph looks. There we go. Okay, so you can see as the L approaches 0, you can see the graph goes way up to a perimeter of infinity, and as L gets big out to the right, it's not as pronounced, but you can see the graph is making its way up to infinity. And so if we want to calculate the minimum perimeter, we found it to be at 8, so I'm just going on either side of 8, and I'll go close to 8, and it'll find our minimum at 8 and 32 right there. All right, let's do example 4. So a farmer has 200 meters of fencing and wants to fence off a rectangular field that borders a straight river. So here's the river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So we want to maximize area. We're going to go fence, and it's rectangular. So fence, fence, fence. Opposite sides of a rectangle are equal, so those two can be x, and here's y, and we don't need any fence along the river. So we want to maximize the area of this. Area is x times y, length times width for a rectangle. And we need another equation involving x and y, and it says a farmer has 200 meters of fencing. So the x and the y, 2x plus y makes up 200 meters of fencing. Now it's easier to get y by itself, so we'll go y is equal to negative 2x plus 200. And so area is x times negative 2x plus 200. Our area function is negative 2x squared plus 200x. And let's get our interval. So x has to be greater than or equal to 0, and it can't go beyond any value that will make the y negative. So y has to be greater than or equal to 0. Y is equal to negative 2x plus 200, which means negative 2x plus 200 has to be greater than or equal to 0, which means that 200 has to be greater than or equal to 2x, which means that 100 has to be greater than or equal to x, so x has to be less than or equal to 100. Okay, so think about that in here. If x goes beyond 100, it will start to make y negative. So those are our endpoints, and we have to now get the critical points and then test critical points and endpoints to find the extreme values. Alright, so a prime is equal to negative 4x plus 200. That exists everywhere. There's no problem points for x, and it's equal to 0 when we set this equal to 0. X equals 50 is our critical point. So now let's test endpoints and critical points. We're interested in the area when x is 0, interested in the area when x is 100, and interested in the area when x is 50. And again, we will take this 0 and let's plug it in here for x. So you can see we're going to get 0 times 200, so that's going to give an area of 0. And then we'll take the 100 and plug it in here. Negative 2 times 100 is negative 200, plus 200 gives 0 in the bracket, so that's going to give an area of 0. And 50, is this going to give us the largest area? We would end up getting 50 times negative 2 times 50 plus 200. Which is, I think, 5,000, right? 50 times 100. 5,000, and that's going to be meters squared. Okay, so we can say, therefore, max area is 5,000 meters squared. Because the 5,000 obviously is bigger than the 0 and the 0 that we got at the endpoints. When x equals 50 meters, and therefore y is equal to, y is negative 2x plus 200, negative 2 times 50 plus 200, which is negative 100 plus 200, which is 100 meters. Okay, and if we do a graph of this area function, the area function was negative 2x squared plus 200x. And our interval is from 0 to 100 in the x directions. Why don't we go 0 to 100? And my max area was up around 5,000, so why don't we maybe go up to 6,000? See what this does. There we go. Okay. And so what I'm plotting there is area versus x values. And this will show when x is equal to 50, we get that max area of 5,000. Okay, and then all other points are below that. Okay, so this will be part 1 of our min-max problems, extreme value problems. I will do another video of the other examples and post that video as well.